Hello, everyone. I'm glad to attend the VICCE and share my recent progress in research. My name is Zuorui from Kyoto University. Today, my presentation is about high-order nonlinear wave interactions from deep to finite water depths with bottom topography change. In recent years, we found the high-order nonlinear wave interactions may be the reason of a disaster, named freak wave, or rogue or extreme wave. This disaster has unusual wave height, and it still doesn't have widely accepted explanation. In general, three kinds of the method have been considered to establish a freak wave model: the linear and the fully nonlinear model and the weak nonlinear model. Considering the accuracy and effectiveness, most researchers concentrate on the weak nonlinear model. In the weak nonlinear model, modulational instability is the main reason to cause freak wave. This can be reflected in the nonlinear Schrödinger equations in this form. And we have a dimensionless number BFI to describing how much the wave energy focusing. In a moving wave chain, the kudosis and the screwness in the statistic about the wave surface elevation have been proved to be related to BFI, and we can also calculate the probability density function of the wave height from the kudosis and the screwness. The kudosis represents 4 wave interactions in third order, and the screwness represents the 3 wave interaction in second order. So finally, the problem of freak wave become how to study the evolution of kudosis and the screwness in a wave chain. In this study, we want to simulate the process water wave entering the continental shelf. So the governing equation should include the bottom chain term in a 2D space. From the nonlinear boundary conditions above, we need to give the expression of wave potential phi and the surface elevation eta. The bottom topography is given by the function of h. H is only a function only about x, because we suppose the bottom varies on y is very, very small compared with x. We suppose the bottom changes very, very mild, and the deep varies very, very slow and explicit. So we can do a variable transform in this form. And then we use multiple expansion method to solve the phi and the eta from the boundary condition. The multiple expansion method help us to divide the phi and eta in different harmonic and different orders about wave steepness. Finally, we can give an NIRS equation in the third order about the wave amplitude A. A is the amplitude about the first harmonic. But we need to know this equation is a partial differential equation. We cannot directly use it. So here we take a Fourier transform to transfer this equation from a partial differential equation into an ordinary differential equation. In this process, in each step, A here is a matrix about the time and space y. If we have an initial date at x0, we can give the wave information by a numerical method by this equation step by step. So here, for example, we will start our calculation in 1D. In 1D, it is a simplified condition. We don't consider the effect from Y. With a given BFI value, we can give a initial wave energy distribution in Gaussian spectra in this form. And with the inverse Fourier transform, we can give the initial wave surface state elevation in time series. It's time series data. And this data is in this point at that side is 0, x0, the initial point. So from the left side to the right side, step by step, we can give the wave date at each point in this process. At each point, it has a wave surface state at time series. And we need to take care that the theta in this equation is a random number about the wave phase. So in each initial wave date, the phase is different. So the final initial wave surface data is different. So we can do the Monte-Carlo simulation. And this is the result of the kurtosis. At each point of the in the x direction in the bottom photography, and at each point it has a time series. So for each point we can have calculate the kurtosis value for the time series activation. And this is the mean value from of kurtosis from 300 samples. We can see from the deep to shallow water as a bottom change. The kurtosis will decrease as water depths decrease. And from the different initial date created by the different BFI, the BFI from the 1, 0.75, 0.5 to the 0.25, as the BFI decrease, the kurtosis value in the deep water also decrease. But we need to say it only happens, it's obvious, very obvious in the deep water. In the shallow water, the effect of BFI is not very obvious. And there is a result about the skewness in the same form of the kurtosis. We need to take care that as the water depths decrease, it seems that there is a critical depth. A critical depth makes the skewness reach its lowest value. That is different from the resulting kurtosis. And we will find the effect from the water depths mostly appears in a high BFI. When BFI is 1 and 0.75, but when the BFI is very low, for example, in the 0.5 case, the effect of the BFI is very, very little. So briefly summary, initial BFI obvious affects the wave instability in deep water. And water depths also affect the kurtosis and has a critical value for skewness. In the same form in 2D, we first give the initial structure and generate the wave surface in this form. This surface is not about x, y in space. It's time t and space y in this section. And we will repeat the process just like in 1D to calculate each section's information step by step. First, we want to verify the flat bottom case. This figure is in x and y, and the value is the kurtosis of the time series. For each point, it represents the crudices of these points time series about surface elevation. And because the 2D case, the calculation takes much more time than 1D, so we only give the mean value from 30 samples. We can see as the initial BFI become larger from 0.25 to 0.5, the crudices become more unstable. A more extreme case happens. This conclusion is the same with 1D, but for scrutiny case, it is a little different. Even the higher BFIs extreme case are more, but for 1D case, the scrutiny is around 0.5, but in a 2D case, despite of the BFI value, the scrutiny is always around 0. It is different. And then for a bottom changing case, we can see the crudices will decrease as water depth decrease. The extreme case in shallow water, relative shallow water, is very rare. That is also the same conclusion with 1D. But we can see for scrutinies, it is different. It seems that water depths didn't affect the distribution of the scrutinies in 2D. So as a brief summary, for crudices, for wave interaction, the 1D and the 2D result are almost the same. But for the scrutinies, the 3-wave interaction, their results are different. What causes these differences? The reason will be part of the future work, and we still need more calculation to explain. That is all my presentation today. Thanks for your attention very much.